Hi guys, in this video I will show you 3 different ways to create these lines between objects. Each method has its own advantages and downsides, and these lines can be used, for example, to create wires between buildings or ivy or even spider webs. And I will also show you a way to create randomized slack for these lines, and also some other neat tricks. So let's get started. So here we have our default Blender setup, and I'll delete the camera and the light because I don't need it for this tutorial. And the first step I'll do is I create a geometry node setup for my default cube. I delete the group input, and now I want some objects on which I instance these lines. So let me create some quickly. I choose the monkey, I duplicate it, rotate it, and I duplicate it again. Now I select all of these and create a new collection. I call these monkeys. And now back in my geometry node setup, I can pull up this collection. So I take the collection info node, and here I can reference these monkeys. And for example, when I disable this group, I can see it because I connected to the geometry output node. And also what I'd like to do is I toggle it to relative. So when I move my object on which the geometry node setup is, it's relative to the position of the monkeys. When I leave this as at original, I can move the monkeys with me, but I don't want this for my wire setup because I want it to stay relative to the monkeys. So yeah. So I'll start with the first and the simplest setup in my opinion, which is based on proximity. So the first step I need to do is I need to realize instances. It's a little bit counterintuitive, but you need to do it for the setup. So realize instance node, and then I distribute some points on my surface. And here you can see these points appearing. And let me quickly toggle the collection back on again. And what I also like to do is switch this to matcap. And yeah. So I want to instance lines on these points. So I pull up the instance on points node and also a curve line. Here you can see these lines appearing. Now I want to randomly rotate these lines, and this can be done with the random value node. I need to set it to vector, and in here I put tau, which describes a whole rotation in radians, and this I can connect to the rotation of the instance on points node, and now you can see every line gets rotated randomly. Yeah, so let me quickly realize these instances, because I want to set the endpoint of every curve to a position based on the proximity to another mesh. So it needs to happen individually. So I need to realize these instances. And now let's quickly create a geometry proximity node. The target is our base geometry we have right here. And now I need to set a position. So set position. And what I want to do is I only want to set the endpoints of these lines because the start point is already connected to a surface. So I can take an endpoint selection node, and here I put the start size to 1, so only the endpoint is selected. I plug this in the selection, and the position I'll put in here. So what you're seeing now is that these endpoints get connected to the closest surface they can find. So right now every line is exactly 1 unit in length. So if I increase this value, you can do it right here, you can see that it started to happen that these lines connect to other objects. So the size of our instances kind of describes a search radius for our proximity. So I can, for example, take a random value node and plug it in here. And here we can, for example, put 2 and 4. So it is a little bit more randomized. And now you can see these lines appearing. So yeah, that's the first setup. It has the advantage of being relatively simple and quite performant. But as you've seen before, if I move these objects here, the lines don't stay stable. So yeah, that's a downside, but it's a really nice result. So yeah, that's an option. So quickly let me put a frame around this and call this proximity method. Okay, so first method is done, and now I will show you another method which solves the problem of the moving objects, so the line stays stable, but it's kind of hard to wrap your head around it, but not really that hard. So okay, so let's create the collection info node again, like we've done before. Select the monkey, set it to relative, and realize the instances. And now I also distribute the points on the surfaces. Yeah, okay. And now the idea is to create some lines and randomly set the position of the end and start point of these lines to the position of these distributed points here. So we can do this with a transfer attribute node. So first let me create some mesh lines. I do this by creating a mesh object with a variable amount of vertices or edges, so to say. So I can take, for example, a mesh circle or a mesh line. In this case, I choose the mesh line. And here I increase the amount for now. And to separate these edges, I can take a split edge node. And now I have separated edges. And because I want to set the position of these vertices, I take the set position node. And now I need to transfer the position from these distributed points. So I take a transfer attribute node with this points as the source. Then I need to switch this to vector, and here I choose index, and I want the position of these points, and then I plug this in here, And right now you can start to see that these lines appear. So the problem right now is that the distribution of these lines isn't really random, even if it looks random, but you have to keep in mind that all these points here have an index. So for example, 1, 2, 3, 4, 5, 6, and so these lines get positioned based on these indices. So to make it more random, I can take a random value node, and if I plug this in here and increase the maximum amount, you can see that it starts to spread and even connect to the other meshes. So what we really need is the total amount of points here as the maximum value. So I can, for example, get the amount with the domain size node. And here I switch this to point cloud and take our geometry, and I have the point count. And we can see we have 362, and I can put this in the maximum value. And right now we have these really cool lines between our objects, and the amount I can control with the count of our vertices of our mesh. And the advantage of this method, even if it is a little bit counterintuitive at first glance, is that we can move our objects as long as our distribute points on faces doesn't change. So if I change this here, our lines change too. Or if I, for example, change the mesh in edit mode, it also changes. But yeah, so if everything stays stable, we can change the position or even the rotation of our meshes, and these lines stay stable. So let's call this the transfer position method. Okay. So right now, every one of these two methods has a little problem. And you can see it right here, for example, that these lines get instanced in our mesh or even go into our mesh from another object. So there's another method which can solve this problem, and which is the most advanced method in my opinion, and has also some downsides that I can show you in a second. So okay, let's quickly disconnect this. And this method is based on raycasting, and we also need these three nodes here. So let me copy them. And right now we have these points here. And again, we need to instance some lines on these points. So instance on points node. And I take the curved line again. And here it is important to keep the length of it to 1. So you can see these lines. And right now we also need to randomize the rotation of these. So I take a random value node. And here it is important to keep the first value at -pi. So 180 degrees minus in one direction and 180 degrees in positive direction, and I need to align our Euler to this vector, which is random. Choose the z-axis and plug our rotation in the instance on points node. So here we have a random rotation again, and with this method we can control the ray direction. So let me first pull up a raycast node, and the target geometry is our monkey collection. So this is the target geometry, and the ray direction is this random vector. So the rotation these instances are rotated is also the rotation of our raycast. And now if this ray hits something, we want to instance align, so I can connect the isHit to our instance on point selection node, and you can see that some lines disappear. And what we also need to take in account is the hit distance, and I can simply plug this in the scale of our instance on points node, and here you can see that these lines get connected. That's why we need to keep the length at 1, so it gets multiplied with the hit distance. And yeah, so to control the amount of lines, I can simply increase it. And yeah, so right now you can see a pretty obvious problem here. There are many lines which get created inside our mesh and we don't want them, and that's the strength of the raycast method, because we can exclude them. And what we want to do is to simply compare the direction of the normal we've hit with the ray direction, and we can do this with the dot product node. So take the dot product, and what dot product does, it is simply compares two vectors, and if these vectors are oriented in the same direction, it returns 1, and if they are oriented in the opposite direction, it returns -1. And we want to take the hit normal into account and also the ray direction, and then we compare these two, so a compare node. And if this value returns greater than 0, it means that our ray hits a surface from the backside. So let me quickly draw this on the screen for you. Here we have the surface of our ray, and it gets in this direction. And here we have the other surface, for example, with a normal in this direction. So let me call this normal, and this is the ray. And here the normal is also in this direction, for example. And this means that our dot product returns a value of 1. And if it, for example, gets hit by a ray of this direction, it may return 0.7 or something like this. And here, if we take another ray from here, which gets a really steep angle but still hits the surface from the backside, it gets a value of maybe 0.1. And if we have a surface from which we shoot a ray in the opposite direction, so maybe for example from here, it may return -1, and so on. For example, if I take a ray from this direction, my drawing skills are really bad, it returns maybe 0.2. So yeah, let me quickly disable these annotations. So yeah, we want to exclude this from our selection right here. So we can do this with a Boolean math node. Boolean math, and we set it to subtract it from our earlier selection, and then we take the result from here and subtract it. And now you can see that these lines inside of our meshes are not getting instanced. So yeah, that's really the advantage of this method, but it also has the disadvantage that if we move this right here, it isn't really stable. So yeah, you have to choose the best method for you. And so yeah, let's quickly the annotations, I need to delete them. Yeah, so quickly put a frame around this and call this raycast method. So these are the three methods, and as a bonus I want to show you a neat little trick to create slack for these lines. And to do this I need to realize the instances, because I again want to create individual slack for every curve, so I need to treat every curve individually. So realize these instances, and then I need to give them more geometry. So right now every curve has only a start and an end point, so I need to resample it. Resample curve. My preferred method is length, so the curves get subdivided evenly based on its length. And then we want to set a position, so let me get a set position node, and we want to offset something on the z-axis. And to access this individually, I take the combine x, y, and z node, and I want to base this on the factor of the curve. So a factor is a value which goes from 0 to 1 for each curve individually. So this can be accessed with the parameter. And if I, for example, plug this parameter in the z value here, you can see that the curve gets displaced linearly from 0 to 1 on the z-axis. But of course we don't want it to happen this way. We want it to happen in a nice little curve. And a trick to do this is, for example, take the float curve. Float curve. Here you can see the linear interpolation, and for example, if I create a curve right here, you can see that this curve starts to appear, and when I invert this by simply multiplying it with a negative value, you can see that we can create this leg really nicely and simple. But the problem with this curve here is that it has really limited control, and what I like to do is to do this interpolation here mathematically, which in my opinion is a way nicer method to do this. So let's quickly do this. The first step is I want to remap the value from 1 to 0 to -1 to 1. So here you can see it, and now I take the absolute of this, which returns positive values for every negative value we have. So now, right now you can see that we have this kind of V shape here, and to create these curves we can simply take a power math node, and here we can put 2 as the exponent in here, and you can see that we have these nice curves which right now have 0 in the middle and 1 at the end here. But of course we want it to be 0 at the end, because here we don't want any displacement to happen, we only want it to happen in the middle, and we can simply subtract 1 from it, and to control the amount of slack I can multiply it with a value. And yeah, so the problem right now is that each curve gets the same displacement in z direction. So even the shortest curves get a really strong displacement, and I want the displacement to be based on the length of these curves. So a way to do this is to simply take the length, spline length, and multiply it with our setup. And yeah, you can see that right now the slack is based on the length. Shorter curves get not so much displacement. And yeah. And also what I like to do is to create random slack for each line. And we can do this to give each of these curves an integer and use this integer as an ID input for a random value node. And to do this, we need to capture our index. So here I want to capture an integer of a spline. And right now I captured an individual index of each spline. And this I can plug in a random value node. And this also can be multiplied with our setup here. And yeah, you can see that each line has now a different slack. So if I, for example, put the maximum value a little bit higher, and this also, we can also create slack in the other direction, but it don't make much sense in this case. So yeah, we can do it this way. And yeah, that's the random slack. So name it random slack. And another neat little trick I want to show you is to create a setup to delete very short curves. Like for example, right here, you can see that we have these short lines which I don't want. And this is really simple. I only need to take a delete geometry node. And I want to delete splines. And for the selection input, I take the spline length and compare it against the value. So again, compare. And if the length is less than a specified value, we want to delete these lines. So here you can see what happens. Nothing happens because I made a mistake. I need to put this realized instances before this, because again, we need to treat every line individually. And right now it should work. So yeah, you can see that only lines above a specific length get instanced. So I name this delete length. And that's the whole setup. So I hope you enjoyed this tutorial and see you next time.